What's up, physics czars? Mr. Sanchez here. I just wanted to briefly walk through this question because there are a lot of layers to it, and I think it is especially challenging because there are multiple parts, and it's not obvious where to start and where to finish, and it's also not obvious what you're looking for. There's a lot of things that are not obvious about this problem. It's very challenging. So, to start with the question, we have a spring that is initially compressed horizontally by 0.25 meters against a 50 kilogram box. Okay? We know that when springs are compressed from their natural length, they will exert a force on the object that they are in contact with. It's one thing. When the spring is compressed horizontally by 0.25 meters against a 50 kilogram box, it just begins to budge. Okay? So the box goes from being at rest to starting to move. Okay? The coefficient of kinetic friction between the floor and the box is 0.3. Remember, there's a distinction between the coefficient of kinetic friction and the coefficient of static friction. And so we're given the coefficient of kinetic friction, which is the coefficient of friction that we would use when the box is in motion relative to the floor. Okay? And that value is 0.3. We do not know the coefficient of static friction, so that's something that we're going to have to look for. Okay? In order to drag the box at a constant velocity with the spring, you pull the spring horizontally so that it stretches by 0.2 meters. Okay? So what this is to say is the spring needs to be compressed 0.25 meters for the box to begin to move. But once the box is in motion, the spring only needs to be compressed, or I guess stretched. Either way, it's not going to make a difference. It needs to be only 0.2 meters from its natural length, which is a little bit less than 0.25, which seems to make sense because the coefficient of static friction is going to be a greater value than the coefficient of kinetic friction. If the objects are not moving with respect to one another, it's going to require more force to get it to start moving, and then once it starts moving, you can exert a little bit less force, as seen by this slightly smaller stretch and compression of the spring. Later, you decide to attach the spring and stretch it 0.5 meters, moving a total distance of 10 meters. So if stretching the spring at 0.2 meters allowed the box to move with a constant velocity, then we know that if we stretch the spring 0.5 meters and we pull the box such that the spring is stretched at 0.5 meters all the time, then the box is going to be accelerating and its motion is going to be changing because there's going to be a non-zero net force. So we now have an unbalanced force scenario. So there's really three different scenarios, three different situations here. So I tried to break it down in the following way. The weird thing about solving this problem, among many things, is that you actually have to start with situation 2 before you start with situation 1 and before you go to situation 3. Okay? So the thing that we need to find is the spring constant. The spring constant is really the thing that is going to allow us to calculate a lot of different things in this problem. So we start by looking at situation 2. And situation 2 has the spring stretched by 0.2 meters, and it has the box moving with a constant velocity. So immediately, this problem sets itself up as follows. We have the spring, right, exerting a force on the box, and we have the force of friction resisting the motion of the box. We have the normal force that the ground exerts, and we have the force of gravity. Okay? These are the forces that are acting on the system, and immediately we can determine what the force of gravity is. The force of gravity must be 500 newtons, and because we know that the force of gravity and the normal force are equal and opposite due to Newton's first law force pairs, We know that the normal force is also 500 newtons, okay? We also know that the force that the spring exerts on the box is equal and opposite to the force of friction because the box is moving with a constant velocity. So we can say that these two forces are equal to one another, okay? And we know that the force of a spring is equal to the spring constant, right? The spring constant times the amount that the spring was stretched by or compressed by from its natural length. So we know that the spring constant, we don't know what that is. We know that the spring is stretched by 0.2 meters, and we know that the force of friction can be expanded to the coefficient of friction times the normal force, while the normal force is going to be equal and opposite to the gravitational force. So we know that in this instance, because we're on a flat surface, the normal force is going to be equal to mg. The reason we write mu sub k is because the box is moving relative to the floor, so we need to use the coefficient of kinetic friction, which we were given in the problem, okay? The coefficient of kinetic friction is used in the friction empirical force law if the objects are moving relative to one another, okay? It's sliding friction. So in this expression, we have everything except for the spring constant. We know how much the spring was stretched by. We know the coefficient of kinetic friction, we know the mass of the box, and we know the gravitational field strength of the Earth. And so we can calculate the spring constant of the spring, K sub S, and we can calculate that to be 750 newtons per meter. So that's telling us how strong the spring is. For every meter that the spring is stretched, it's going to exert 750 newtons of force, okay? Once we have the spring constant, right, we know that F sub S is equal to K sub S times this. So we could say we know that the spring force is equal to 750 newtons per meter times the amount that it was stretched by, 0.2 meters, which gives us 150 newtons, okay? And because we know that the force of friction and the spring force are equal and opposite, we know that that is also equal to 150 newtons, okay? So that is really how you start this problem. You start with situation 2, recognizing you have a balanced force situation, constant velocity. You can determine the spring constant of the spring. Then you can come back to situation 1, and we're going to be looking for the coefficient of static friction of the box. Okay, a number between 0 and 1 that is unitless in nature. And so in this instance, this is actually incorrect the way that it's drawn. This is not correct. My apologies for that. In this instance, we have the spring that is, oh, actually, wait. No. Yeah, it was correct. Whoops, sorry. Some visualization things going on there. Okay, so the spring is pushing on the box, and the force of friction is trying to resist the object's tendency to move. And so we have this force diagram horizontally, which is the more interesting area. And then, of course, the normal force and the gravitational force cancel out. Okay? So now we have a situation where the spring is compressed by 0.25 meters against a 50-kilogram box, and we're trying to find this. We're not trying to find the spring constant. We already found the spring constant. We are trying to find the coefficient of static friction. Okay? Static friction meaning the objects are not moving with respect to one another. Okay? So we use the same exact argument that we used here. We know that the force of friction is equal and opposite to the spring force. Okay? And we don't know what this is just yet. So we can expand this expression just like we did here, and we say the spring force is, the spring force is equal to K sub S times the change in X, and the frictional force is equal to mu sub S times mg. The reason that we're using mu sub S this S represents static. It is the coefficient of static friction, is because the box was going from not moving to moving, so we have to use static friction, okay, because the object was not in motion. The objects were not in motion relative to one another, okay? So we use the same argument here as we did in situation 2, except this time, since we know the spring constant, we know the spring constant right here, but we don't know the coefficient of static friction, so we can use this expression to isolate the coefficient of static friction. Okay? And once we do that, we can solve for that straightforwardly, and we can find out that the coefficient of static friction is 0.375, which makes sense. Okay? It makes sense because the coefficient of static friction should be greater than the coefficient of kinetic friction, which is 0.3. So we could say mu sub s equals 0.375 and mu sub k equals 0.3. They should be close to one another, but of course we have the fact that the static friction is greater than, which makes sense. Okay? So finally, now we just get right into, because we know that the coefficient of static friction is 0.375, we can now calculate, because we know that the spring constant is 750 newtons per meter, we know how much the spring is compressed, we know that the spring would have to exert a force of 188 newtons. So we got that there using this same type of argument, except we use 0.25. And finally, because we know we have a third situation, you attach a spring and stretch the spring 0.5 meters, okay? Box, therefore, begins to accelerate. Okay? The box begins to accelerate. So now that the box is accelerating, we know that the box is accelerating because because in the previous situation, we determined that the maximum force of friction is going to be 150 newtons. Once the object is in motion and it's sliding, you've now reached the maximum amount of friction that that object can experience. The faster you pull it, it's not going to experience any friction because, as we saw in the friction lab, friction doesn't depend on how fast the object is moving. It's going to reach some maximum value, and that value happens to be 150 newtons, okay? And so we know that the force of friction is 150 newtons from the previous situation, and we use really the same argument that we used in the other two situations, which is the net force is the difference between this spring force and this force of friction, and so we just take these two values, we calculate them empirically. The spring force is going to be 300 newton. Oh, no, this is a typo. Wow. Oh, goodness. My apologies. This is 750 newtons per meter. Really good that I made this video because this is really helpful for me as well. Okay, so this is 750 times 0.5, which is going to be, oh, goodness. Now these numbers are going to change. Uh-oh. Here we go. Okay, 750 times 0.5, okay, which is going to be 375 newtons. 375 newtons, okay. I just lost double checks my work standards, okay. And this is going to be 375 minus 150, which is going to be 225 divided by 50. It's going to be 4.5. Wow, significant difference. It's going to be 4.5. The acceleration is going to be 4.5. 4.5 meters per second squared is what I calculated. Okay. All right, so this 750 corresponds with this, so that's the spring constant. That was just a typo, and that's 375. So I try to not use numbers until the end. Okay, so we have the spring force, we have the force of friction, and we have the mass of the block. Okay, the good news is we can just sort of not worry too much about the numbers. I'm not going to review the motion analysis because I think you guys are proficient at that. So I'm just going to sort of plug in these new numbers. So we have 2 times 10, the square root of 2 times 10. Let me just Desmos this out real quick. So we have the square root of 2 times 10, which is the displacement, and we're dividing that by the acceleration, which is 4.5. Okay, which is about 2.1 seconds. Okay, and therefore the time changes 2.1 seconds. Oh no, and that also changes the acceleration, which is 4.5 meters per second squared. 4.5 times 2.1 is roughly speaking 9.5 meters per second. Okay. The motion analysis isn't really as important as to be fair, is not as important as finding the coefficient of static friction and the coefficient of kinetic friction. It's just something that you can do to get extra practice, calculating the spring constant of the spring, which we then correctly implemented here. And we know how much the spring is stretched by. We know the net force, take the difference to find the total net force, get an acceleration of 4.5 meters per second. And finally, we come to see that the motion analysis is as follows. And so I hope you found this video helpful, especially because we realized there were a couple clerical errors that were in the problem, probably from a former iteration of when I was solving the problem. So anyways, I hope you all have a great day, and I hope you found this helpful. And if you have any questions, don't hesitate to reach out, okay? See you next time.